Okay, so today we're going to start 4.2 reduction of order in section 4.1, which is the discuss some general results of theorems about how different equations. We talk about how to solve how different equations in general. In this chapter, we just deal with linear differential equations. So we started from linear homogeneous differential equations of higher order. And we know that we need to find the linearly independent solutions first for the homogeneous differential equation. Homogeneous means you don't have any terms of x itself or constants. All the terms are the derivative of y and y itself, the derivatives of y with some coefficient functions on each. So then after you find a fundamental set of solutions for the differential equation, you just make the linear combination of them. That will give you the general solution of the differential equation. Okay, that's how you solve a homogeneous higher order linear differential equation. A fundamental set means the solutions are linearly independent, and we can use the Wronskian to determine whether the set is linearly independent or not. So that's about homogeneous equations. If we want to solve a linear higher order non-homogeneous differential equation, then we need to solve the associated homogeneous equation. The non-homogeneous differential equation means the right-hand side is not zero. So in addition to the y and the derivatives of y's, you got some functions f, x, and they put on the right side, which is not zero. To solve that equation, then you just find out solutions for the homogeneous equation, the associated homogeneous equation. We just drop the right-hand side to put zero on the right side and solve it. And then you need to find a particular solution to the original non-homogeneous equation. Okay, so you find the general solution to the associated homogeneous equation, and then you find one particular solution to the non-homogeneous equation, and then you just add them up. So that will solve the non-homogeneous higher order linear differential equation. Okay, so it's getting a little more complicated so far, and we have not even discussed how we solve, homogeneous linear higher order differential equations in general. And we also have not discussed anything about, finding a particular solution for the non-homogeneous equation. So we have to break up into different parts to solve, a general linear higher order differential equation. So we're going to discuss those topics one by one in the following. And again, there are a lot of steps involved. One thing we discuss in this section is called the reduction of order. So suppose you already found one solution for a homogeneous second order differential equation, then we can use the technique of reduction of order to find another solution for this equation, which is linearly independent with the given solution. Okay, and then that will give us two linear independent solutions. So then essentially we solve the whole the equation. And later we're going to discuss how we actually start to find the first solution for the homogeneous equation. All right, so we just do these steps one by one. Each step involves some techniques. Okay, so this 4.2 is just one step in this procedure of solving a differential equation, linear differential equation of higher order. Okay, so so let's just consider the linear second order homogeneous differential equation of a2 of x y double prime plus a1 of x y prime plus a0 of x times y equal to 0. So this is a homogeneous differential equation because the right hand side is 0. So suppose that y1 denotes a non-trivial solution of the differential equation. Okay, we know we always have a trivial solution of y equal to 0, the constant function, but we're not interested in that. So y1 is not trivial, and then of course y1 is defined on an interval I. So we want to find the second solution y2 of the equation linearly independent y1 on the same interval I. So that essentially means y2 is not equal to a constant c times y1. So they are linearly independent. That's what it means. So in other words, we can write y2 equals a function u times y1. Okay, where u is not a constant. All right. So if you just divide y1 on both sides, u is just a y2 or y1. We don't know what y2 is, but suppose we just assume another solution y2. So we know there's such a solution y2. So we just divide y2 by y1 to get the u. Okay, and y1 is given. So then we can actually change the equation to another one for u instead of y. Okay, and the reduction order means in this way the equation for u will be first order instead of second order if you do this substitution. Okay, so we're going to start from an example and show how to proceed with this procedure. So given that y1, which is e to the x, is a solution of y double prime minus y equal to 0 on the interval from negative infinity to positive infinity. Okay. Use reduction of order to find the second solution y2. Okay. So we know y1 equals e to the x is a solution of the differential equation, and we try to find another solution of the differential equation y2 linearly independent of y1. All right. So we just start from substitution. Y2 equals u times y1. Okay. So that means u times e to the x. And then we take the derivative of y2 using the the product rule. So this is u times e to the x. A product of two functions. When you take a derivative, you just use the product rule. So that gives us, u prime e to the x plus u times e to the x prime. But the derivative e to the x is just e to the x. So we got u prime e to the x plus u times e to the x for y2 prime. And then you just take the derivative of y2 prime to get the y double prime. And so we got two terms, u prime e to the x plus u times e to the x to take the derivative. All right. Again, we just use some product rule again for each. Because u prime is a function of x also. So then in the first part, you just take the u prime, the derivative of u prime times ex plus u prime times ex prime. Once again, ex prime is just e to the x, okay? And for the second part, namely the derivative of e to the u times e to the x, we already did them when we differentiated y2 prime, okay? So basically, u times e to the x is just y2. So we already got it in the first step. That is u prime e to the x plus u times e to the x. So then now we can combine u prime e to the x to get a 2 times u prime e to the x. Okay, so the whole thing becomes u double prime e to the x plus 2 u prime e to the x plus u times e to the x. All right. So this whole thing is just product rule. And then we can plug in this y2 double prime, y2 prime, y2 into the different equation and then rewrite it in terms of u and u prime, okay, or u double prime. So just plug in y2 double prime and y2 in the equation for this simple case. So then we get u double prime e to the x plus 2u prime e to the x plus u times e to the x from y2 prime double prime minus u times e to the x, which is y2. So you can see the last term cancels. So what is left is just u double prime e to the x plus 2u prime e to the x. And then we can divide by e to the x on both sides. So that gives us u double prime plus 2u prime equal to 0. So now we're going to do another substitution. We're going to use w to denote u prime, since we know u prime is a function of x. So we just use another notation. Okay. Then what it means is when you take the second derivative, u it's just the first derivative of w. All right, because w is just the first derivative of u. Okay, so then the equation becomes w prime plus 2w equal to 0. Okay, so you can see it becomes the first order differential equation that we know how to solve it easy. We can do it by separable by separating variables. Okay, we learned it before. Okay, for example, you can also use the formula for linear first order differential equation. Okay, so if we do it by separating variables, we can move 2w to the right, and it becomes negative 2w, and we can rewrite w prime as dw over dx, and then divide by w and multiply dx on both sides. Then we're going to get the dw over w equals negative 2 dx. Okay, so we just separated the variables and then integrate on both sides separately. So on the left hand side, we're going to get the natural log of absolute value of W equals negative 2x plus C. All right. We have done those so many times. So I'm not going to, explain too much. So if you take the exponential on both sides, it essentially becomes W equals some arbitrary constant C prime times e to the negative 2x, where C prime here can be both positive and negative. So that will take care of the absolute sign. Okay. So then, because we define the W from U prime, okay, so we need to go back to find the U, okay, from here. So U prime is just the C prime times e to the negative 2x. So what you do is just integrate to get a U. So U is just the integral of C prime e to the negative 2x. So if you do that, you're going to get negative C prime over 2e to the negative 2x. Okay. Okay, so we don't have to worry about the arbitrary constant here because we only need to find the one of those u's. Okay, so we can just drop the arbitrary constant. And we can choose actually C prime to any number in here. So if we choose C prime equals -2, not -0.5, I'm sorry, then the U just becomes negative of -2 over 2, which is 1 times e to the negative 2x. So that's e to the negative 2x. So once again, we can choose that because we only need one of those u's. Okay. So then we get the y2 because y2 is just u times e to the x. So that's e to the negative 2x times e to the x because the u is negative e to the negative 2x. So that will give us e to the negative x. So at the end, the solution for the problem is just e to the negative 2x. So that's another solution of the differential equation linearly independent of y1. Okay. So that's how you reduce the order from second to the first in finding, another solution of the homogeneous equation from the given solution. All right. Okay, so does it make any sense? All right, any questions about this example? Okay, so from this example, we can actually see this kind of procedure can be applied to a general homogeneous second order linear differential equation. So let's just build a general theory for the reduction of order in second order linear differential equation, all right? Homogeneous differential equation. So this is the general case. Again, we start from the equation a2 of xy dot prime plus a1 of xy prime plus a0 of xy equal to 0. So that's a general second order linear differential equation. It is homogeneous. And we will start to rewriting it in standard form by dividing by a2 of x for the whole equation, and that of course will require a2 of x not equal to 0. Okay, in the domain we consider. So then we get the standard form y dot prime plus p of x, y prime plus q of x, y equal to 0. Remember, we did the same thing when we try to solve first order linear differential equation. So here, p of x just a1 of x over a2 of x, and q of x just a0 of x over a2 of x. And they're both continuous on the interval I, okay. So this is the assumption and it's required. Okay, then we can start with the procedure. Suppose that we already know y1 of x is the solution of the equation and it's not 0, for the whole interval I. So we also require y1 is not 0. All right. So then we will just deal with the standard form of the equation, and let y2 is equals u times y1, where u is another function, it's some function, okay? Then we just do the same procedure again as in the example. We find the derivative of y2 and the second derivative of y2, and we try to convert the equation into one with u, and then from that we can solve for u and then obtain y2. Okay, so we don't know why both y2 and u, but we know though they exist and they are functions of x. So just to do the derivatives using product rule again, everything is just parallel to the example we did. So using product rule for y2 prime, we get u prime times 1 plus y1, u prime times y1 plus u times y1 prime. So this time, y1 is just a known solution for the equation, instead of e to the x in the previous example. All right. And then we just take the derivative of 2 prime to get the y2 double prime. So again, we got two terms, and we just use product rule for each term when we take the derivative. So namely, we need to take the derivative of u prime times y1 and the derivative of u times y1 prime. So after applying the product rule, we get u double prime y1 plus u prime y1 prime plus u prime y1 prime plus u times y1 double prime. Okay. And then you can combine the two terms in the middle to get the 2 times u prime y1 prime. Everything else is the same, keep it the same. So then, now we can plug in y2 double prime, y2 prime, y2 into the equation, because we already assumed that y2 is another solution of the equation. All right. So if you do that, so you're gonna get u double prime y1 plus 2u1 u prime y1 prime plus u times y1 double prime. So that's just the y2 double prime plus p times u prime y1 plus u times y1 prime. So that's just the y2 prime plus q times u y1. All right. So plug in everything related to y2. And then we're going to group the terms. We got the 6 terms. Basically, if you distribute the p in the second part, okay. So you got the p times u prime y1 plus p times u times y1 prime. All right. And then we're going to group 3 terms. U double prime y1 plus 2 times u prime y1 prime plus p times u prime y1, and then group the other 3 terms, u y1 double prime p times u y1 prime plus q times u y1. So you can see the three terms, we have u in common that can be factored out. So if you do that, we get u times y1 double prime plus p times y1 prime plus q times y1. Okay, and these three terms. Then you can see, because y1 is the solution of the equation, then obviously y1 double prime plus p times y1 prime plus q times y1 equals 0. So that's why we group those three terms together. So then the second part of the equation on the left is just 0. U times 0 is just 0. So you're only left with the first part to solve, which is u double prime y1 plus 2u u prime y1 prime plus p times u prime y1 equal to 0. Okay. Again, remember y1 is given in the problem, so we actually get the equation for u double prime and u prime. If you look at the equation left, that's the only thing we don't know. So we just assume, or denote u prime by w again, and solve the solve u. Okay. Or w. So then u double prime is just w prime. And then, we can write, it as dw over dx. So now we can separate the variables in the equation to solve for w. Okay. So we got dw over dx times y1, which is u double prime times y1, equals negative 2y1 prime plus p times y1 times w. Remember, w is u prime. You can see from the equation, the two terms, the second term and the third term on the left, as u prime that can be factored out, which is also w. And we already put those two terms on the right. Okay. So then you can see the only thing we don't know is just w. y1 and y1 prime, p, all of them are given. So what you do, just divide by w and multiply by dx, and also divide by y1 in this case on both sides. So then we get the dw over dw over w equals negative 2y1 prime plus p times y1 over y1 dx. So then you can just integrate on both to solve it. So again, we get the natural log of absolute w equals the negative integral of 2y1 prime plus p times y1 over y1. And we can break it up into two integrals. If you break the numerator into two. So that gives us negative 2 times the integral of y1 prime over y1 minus the integral of p times, okay. If you cancel y1 in the second term, okay. So again, the first term, the integral of y1 prime over y1, if we integrate it, you get natural log of absolute y1, all right? So then we can rewrite the equation as natural log of absolute w plus 2 natural log of absolute y1. If you move negative 2 natural log of absolute y1 to the left, becomes positive. So that will equal to negative integral p. Okay, so we can use the property of logarithms to rewrite the 2 times natural log of y1 absolute as natural log of y1 prime. Okay, so just gives you exponent the 2. Just gives you exponent. So then we can also combine the two natural logs to get the natural log of absolute W times R1 prime equals the negative of integral of P. So then, we get W times R1 prime equals the e to the negative integral of x. Again, we don't have to worry about positive negative, when we take the exponential both sides. We don't have to worry about the opposite constant also, because we need to just find one such W, okay? So then you divide by one square, because W equals e to the negative integral P over 1 square. So, but that's just the U prime. So you integrate this whole thing to get a U. So U is just equals integral of e to the negative integral P over y1 squared. So then y2 is just the U times y1, which is y1 times the integral of e to the negative exponential of negative P over y1 squared. So this is the formula. So we'll stop here and we're going to continue next time.